Hello and welcome to this webinar. My name is Adil Masood and I'm the coordinator of FlexIC prototyping services at IMEC. I will be your host for this latest edition of the webinar series on Pragmatic's FlexIC technology. The series started in 2023 with 2 episodes where we introduced the Pragmatic's flexible integrated circuit technology and its advantages over the more traditional silicon-based technologies. And in the second webinar, we took a deep dive into Pragmatic's FlexIC technology with details on their Gen 2 PDK. These episodes are available on the YouTube, and this webinar will be third in this series. Since then, the prototyping services was enabled, and we took these technologies to many small companies, SMEs, and innovators from around the world. We already taped out 4 multi-project wafer runs, and also started a dedicated mask service. Now, today's episode is special because since then the technology has evolved, and now Pragmatic has taken this technology to new height with their Gen 3 or third generation FlexIC platform. Now, I will leave it to the presenters to deep dive into it. Let me introduce the presenters. We have Dr. Francesca Botacchi. She received a PhD in experimental solid-state physics at Imperial College London, working on organic optoelectronics devices, and has over 10 years of experience in flexible electronics. She joined Pragmatic Semiconductors in 2022 in the commercial team as a senior account manager for foundry customers. Our second speaker is Suman Balaji, who received a master's degree in system on chips design at Lund University, Sweden, focusing on integrated circuit designing. He later did a research internship at IMEC, focusing on digital IC designs and also on related flows for FlexICs. He joined Pragmatic Semiconductor in 2021, and he's currently a senior engineer in design enablement group. So now I give the floor to the presenters and wish you a great webinar.
Thank you very much, Adil, for the introduction, and thank you everyone for joining this webinar today with me and Suman. So basically we will present both. We will switch a few times. I will start with an introduction about the company, Pragmatic, and what we do. Suman will then dive into the technology details of the new platform. Then I will continue with some example of use cases and applications, and then Suman will conclude with the more practical details of how to join the run and how to access your practice services. So I think we can make a start. Good. So Pragmatic Semiconductor, we specialize in flexible semiconductor technology. We are based in the UK with a headquarters in Cambridge, and we have a manufacturing line in Durham, in the northeast of England. This is the first UK 300mm wafer fabrication line. And we provide 3 main services. First one is manufacturing services, which is basically foundry services. Then we can also support new product developments with engineering services. And we have our own standard products, which are all from the RFID, from an RFID portfolio. So what do we do at Pragmatic? Sorry, next slide. Yes, so we manufacture flexible integrated circuits. So this, we call it FlexIC. And these are low-cost, ultra-thin, and flexible chips, which are a more sustainable and cost-effective alternative to silicon. And in terms of functionalities, this can enable connect, sense, and compute capabilities, all integrated in the same chip. So what are the main advantages of using FlexIC technology? So first of all, there's a big trend in miniaturization at the system level. And for this, of course, novel form factor, especially thin and flexible form factor, is required. And this is a great benefit that can be unlocked with FlexIC technology. You can either reduce the system of by using FlexIC, or reduce existing system, or you can even add more functionality within the same space. So this is two different advantages of the possibility of miniaturizing electronic solution at the system level. The second advantage is, of course, about IoT. IoT is getting everywhere nowadays, and with FlexIC, we're really driving intelligence and connectivity from the edge all the way to the item. We want to bring intelligence at the item level. And of course, to do so, the technology needs to be lower cost, needs to seamlessly integrate with the product, and needs to add extra functionalities. And it needs to be also sustainable. So the third point is about sustainability. If we want to add intelligence and electronics to everyday objects, then of course we cannot add substantial carbon footprint to products. So our smart manufacturing, it's really key to enable more sustainable solutions. So in terms of manufacturing, this is just a very quick video of our manufacturing line. Is our new 300mm wafer line in Durham. And as I said, this it has a capacity of billions of chips per year, with a very rapid cycle time of less than a week in volume, and a turnaround of tape out to wafer delivery of just a few weeks. And all of this is done in a more low carbon and more sustainable way. And this is mainly because of the different material and processes that are involved. We don't use silicon, so the temperature are lower, there's less energy, less waters, and fewer chemicals involved in the process. And altogether, it makes it a more sustainable and lower carbon manufacturing technology. So as we say in the title of this webinar, this is about the introduction of a new platform, which is, so it's not just about PDK, that Suman will go into the details soon, but it's the whole platform. So the platform, of course, it consists of the new PDK, but it is also compatible with existing EDA tools. It has a standard cell library, and it's basically it's what enables the fabrication on 300mm wafers, in a more sustainable and low carbon footprint with thin and flexible chips. So all of this basically makes the platform, and I think now Suman can really dive into the details of what the PDK is about and what are the main advantages over our previous second generation technology.
Okay. Thanks, Francisca, for introducing the new FlexIC 300mm fab and the platform. So I want to take deep dive into the new platform we have, which we call Gen 3 platform. At a top level, if you see the components that's available within the platform or the PDK, it's N-type TFTs. Then you have dedicated resistor layer. Then you have possibility to build capacitors, which are MIM caps. Then you have metal layers, which can be used for interconnects. There are 4 metal layers. The total thickness of our wafer you see is around 37 micrometer. As Francisca introduced, all our wafers are 300 millimeters now. You can, because this is flexible, you have a bend radius of almost 5 millimeter in the technology. So what we have seen with our projects, with some of our digital projects, is compared to the previous HelVillain 2 technologies, some of you have used before, we have seen almost a 10x digital power reduction and a 3x area reduction compared to the previous technologies. So here I would like to briefly touch upon how we manufacture the wafers in our Dharam site. The substrate is glass. It uses traditional silicon process where we use deposition method, which can be either PVD or ALD techniques for deposition. Then we photo pattern it to get the patterns. We have many mask layers. Then once you photo pattern this, then we go with dry etch or wet etch. We use dry etch for some layers. We go for wet etch with some of the layers. So as Francisca said, there's no silicon materials used, and we don't use any high temperature in the process. The process flow is much simpler compared to traditional silicon flow. Here, I would like to touch briefly upon what differences have occurred from our previous technology to the new Gen 3 technology. So as you see, an image here shows a comparison between the 200 millimeter wafer and the new 300 millimeter wafer. That's a major change. You get more number of dies or chips per wafer. At the top level, in terms of N-type TFTs, we have the width has been decreased for a single transistor to 1 micrometer. The length of a maximum dimension transistor is decreased to 1.2 micrometer, but this is only for a single transistor. You could always connect these transistors in a series or parallel to get higher width or higher length devices. The major change is field effect mobility, where you see it is almost doubled to the previous technology. In terms of resistors, the pitch, which is the width and the spacing between the resistors, have been massively decreased to these numbers. So you can tightly pack resistors together now, so you can save a lot of area. In terms of temperature performances, our resistors are NTC devices. You see a drop of 0.8% per degree rise in temperature. In terms of WIM caps that I said, you see there's almost a double increase in capacitance from 2.7 femto to 4.5 femtofarad per micrometer square, which means you can have more capacitance per unit area in the new technology. In terms of interconnects, as you see, all the pitches of metal layers have been massively decreased. The routing pitch is now 4 micrometer. The widths and spacing of metal layers are also decreased. In terms of packaging, the passivation layer thickness has been increased to 2.5 microfarad. The topmost metal layer that you would use for external world connection has been increased to 1.5 micrometer. The bend radius is still the same. Yeah, this is the new platform at a top level. Yeah. Next thing is what type of devices you get within the PDK. All our transistors are N-type transistors. These transistors are enhancement mode transistors, which means they have positive threshold voltage, and you need to give a positive voltage at gate and source to turn on these devices. In terms of resistors, we have a dedicated, very high layer for sheet resistance, which is almost 200 kilo ohm per square. You don't see this high resistance in silicon technologies. So this value is very high, which you can use it for your applications. In terms of capacitors, MIM capacitors, which is built using the two metal layers in our stack, it comes to about 4.5 femtofarad per micrometer square. And as you see, this is a graphic of our wafer, the substrate. After the glass, it's a substrate. Then we start all the processes that we went through previously, like deposition, photo pattern, then etching, to get first front end of the line materials for resistors and transistors. Then we start building our metal interconnect layers. Those are four layers we have. Then the topmost you would get an RDL connect. RDL is made of aluminum right now, and the thickness, as we discussed, is 1.5 micrometer. Next thing is about the process design kits, what components you would get, what a designer would see once he or she gets the PDK. So you would get OA-based cells for everything. The P cells that we discussed, the transistor, resistors, and capacitors available in the library. So you would get a schematic view, you would get a layout view, you would get a symbol view, you would get P cells option where you can automate stuffs. Then you would get models. Models are a major part to simulate the circuits, see if your application is fit. Here in the models, we would give the corner models, which is typical fast, slow models for all the components. Then we have Monte Carlo models also available. Then we have temperature model included. The temperature range is between -20 to 85 degrees Celsius, which we have characterized and put into the models. Then you would have safe operating region assert files, where if you use these files, you would get warnings if you exceed so current or voltages within the components. Then coming to the rule decks, you would get DRC LVS specs rule decks, where you can, once you finish your layouting, you can run these checks using the decks. You would get setup and script files to make sure the installation happens properly, and you would get all sorts of layer map stream of files to extract your GDS and send it to fabrication. With this PDK, you would also get a wide variety of documents. It's exhaustive document materials that you would get to go through the technology, understand more about the models, which is very exhaustive. Yeah. So once you get the PDK, that is this part of the slide, you could start designing stuffs to see if the application suit you. In terms of design tools, currently we support Cadence and Siemens. For analog design, it would be Cadence Virtuoso. It's the schematic editor and the layout editor. Then for simulating the circuit, it would be the Spectre platform from Cadence. For digital designs, where we give the stand cell libraries, it would be Genus and Innovus for synthesis and place and route. Then for Tempus for timing sign-off closure, Conformal for LEC checks. You could also do RTL design and verification with Xcelium tools. For Siemens, as we discussed, the decks that we give away is the DRC LVS specs are Caliber. So you need to use Caliber tools to run your sign-off checks. And one more point, all these tool sets are available within the EuroPractice offering. So if you're already a EuroPractice member, you would have access to these tools. So it's easier. Okay. Yeah. One request we have seen since our Helvellyn 2, the previous platform releases, we are getting queries or interest saying they will also need stand cell libraries. So it would enable you to design stuffs faster. So with this Gen 3 platform, we would also release the stand cell libraries. The stand cell libraries is a complete set of almost having 100 cells in the library with various drive strengths like X1, X2, X4 drive strength cells, various frequency specs for flip-flops, and different drive types. What drive type means? Let's say these two is an example from the library. If you see, because our technology only use N-type transistors, the pull-up part usually is a resistor. So this is a resistive load logic. If you see this logic, both these circuits are inverters. If you see this, the output stage is also replaced from a resistor to N-type transistor. So this drive type we call pseudo CMOS drive type. So these two are different drive type cells available in the library. So some advantages between these two drive type logics is when you use pseudo CMOS load, your rise time and fall times would be almost symmetrical. So it would help you in certain applications. Whereas the rise times and fall times when you use this technology would, the rise time from 0 to 1 would be very high compared to the fall time from 1 to 0. So there are many combinational cells that are mentioned here. All the basic cells that's required to design circuits is there. Then you have sequential cells like flip-flop, latches, flip-flops with clear. Then all the libraries are characterized at various PVT corners. So different across various temperature ranges, across various voltage ranges. So you would get a wide variety of .lib files with this. The package of the standard cell library consists of .lib files, .lib, .v Verilog files, and QRC tech file. Very helpful when you do synthesis, place and route with Cadence tools. All our standard cells in the standard cell libraries are 5T track cells. HIO cells, right now we are designing and testing it. It will be available at a future date right now. So in that library, we plan to release digital IO bidirectional cells, analog through cells, and core IO. This would not come out now, but later in the year, there's a plan to release this as well. Yeah, I have a short video here to show you an example in the design environment. So I've tried to instantiate some of the components available within our PDK, like the transistors, the resistor, the capacitor. All the design type is similar to other PDKs the designer should use from silicon foundries. So you have P-cell option when you try to instantiate cell, where you can change the width length of the transistors. For resistors, you could again change the width, length, resistance value. Once you build your schematic, you can change all these parameters. You have various options for transistors as well. It's temperature modeled. Once your schematic is complete, you would go to layout. Again, here we have P-cell options to vary the width, vary the length. Then the transistor you can implement using multipliers or fingers options, which is also available. You can instantiate resistors. Again, resistors are built with dedicated layer, having plus minus connections in a metal layer with different shapes also. So resistors to save area, you can draw resistors from P cells at different shapes. Then, as we discussed, we have metal interconnect layers, which can be built with wires, connections, everything possible. Yeah, this is an example, but yes, Francisco.
Yes, that's back to me. Thank you, Suman. So yeah, this is, I would like now to go a little bit into kind of some use cases or some examples, functionalities that you can use our PDK for. So this is these are some IP blocks that we have developed, and this is to give you kind of a flavor of what type of performance and functionalities, can be achieved with our PDK. So here you can see on the left side, in the green squares is more about RF front end and more like wireless communication designs and protocols. Then on the right side is more about sensor readout system and analog front end, where you can you can design ADC amplification, multiplexers, and either on-chip sensing, like for example temperature sensing or moisture sensing, I believe, but then also off-chip sensing, like integrating with external sensors, like piezo, piezo material for like pressure sensing or other type of external sensing. It can be combined with like digital peripherals and interfaces, like I2C, SPI. These are all blocks that we've done many times. You can design drivers for LED, for display applications, and even more complex, let's say, microcontrollers or logic control units like the red blocks. Those are more kind of advanced and complex systems that we've demonstrated, which say are more exploratory, but it's also to give you an understanding of what actually, what's the possibility, how far you could push the boundaries in terms of complexity and functionalities. So on the left side, there's like a list of typical design blocks with some ranges of performance that you can aim. And I would say one thing to add, at the very end is also passives and interconnects, which is something that we're seeing a lot of value recently, being able to basically achieve identity interconnect with the passive functionality is something that is really gathering a lot of interest recently for a lot of applications. So if you go next. So as I said from the beginning, our main aim is really to add intelligence to everyday objects at the item level, and to do so, we need to be lower cost and thin and flexible to integrate into existing products. This can be done with a different variety of designs. If you think about RFIDs, this can be applied to smart packaging or for circular economy, for example, to help reduce food waste or to help track and track the life cycle of products. We can use our technology all the way to healthcare application, to wearable devices in the consumer electronics space, and all the way to microfluidics and sensor integration. So let's start with, I think, so this is our first NFC product that we've just released a couple of weeks ago. Again, is to give you an example of what can be done. So this is something that is already available, basically out there. You can, it's something that we can release samples and that we are already manufacturing at volume. So this is an NFC chip that basically contains a unique ID, and it's thin and flexible. It's basically a like-for-like, I would say, alternative of silicon, but more cost-effective and more sustainable. In terms of more technical specification, this chip is based on HF RFID design and is compatible with NFC Forum Type 5. It's a 6mm square design on Gen 3 technology, so it's our latest release, and it has unique ID, like a read-only memory with a unique ID, and which makes it compatible with Android and iOS. So it's really let's say suitable for consumer engagement applications, and where you want to kind of connect the digital and the physical world from a consumer point of view. RFID is not the only application that you can achieve. We see, let's say, these are the three main areas, like a stream of use cases that we're also focusing our own internal development at Pragmatic. The first one is high-density interconnect. Especially recently, we've seen a lot of interest from trying to design just maybe a simple connector, that you can take advantages of the multi-layer routing and also of the smaller line width and pitch of the interconnect of the routing, and really add functionalities like passives, like some active signal conditioning, for example, to really design a smart version of a flex PCB, basically. That it's really suitable for, let's say, consumer electronics, or for applications where there's a space constraint and you really need to make use of all the 3D space in a smarter way. So that's the first one. Second one is about sensor integration. Again, we can enable an easier integration with existing products. So we can bring visualization of the signal right at the sensor. This is especially for wearable sensors, for example, that will simplify the complexity at the from the processor unit, and really bring all the as much as possible of the signal conditioning, the signal processing right at the sensor. So this is also a big advantage that makes use, is basically using our thin and flexible form factor. And then in general, as the FlexIC platform Gen 3 is really designed for mixed signal devices. So the hope is that people will design fit for purpose circuits that can be optimized for cost and for size, for really what is required, with all the connect, sense, and control capabilities that would make it useful for a variety of different applications. So first, I would like to dive into the, let's say, high-density interconnect and more consumer electronics requirements. Again, there's a trend that is moving from rigid to hybrid to fully flexible systems, and this is to make a better use of 3D space, to really add electronics to system where electronics, were not present and was not possible with conventional rigid systems, and also to add intelligence from the edge all the way to the item. And again, in order to do so, we need to be able to integrate with everyday object, with every already existing products. And so this is something that we're really focusing our development, to be more and more compatible, and to simplify integration to bring item level intelligence. And so another example of going beyond these examples is, for example, an example of a smart glass, where, sorry, if you go next. Yeah, so here you see, this is an example of where adding a smart interconnect might be key to simplify the system at the product at the system level. In this case, is an example of a smart glass with a flexible chip that is connecting two rigid pieces, to rigid PCBs in the glass, but you're really just adding the flexible chip where it's required for bending and flexibility purposes. But it's not just a connector. You can well, first of all, you can have a very high density routing with a very fine pitch, but you can also add extra functionalities. You can offload passives and also some active blocks from the rigid PCB into the flexible connector to really reduce as much as possible the size and the cost of the rigid components, and so their overall system will get streamlined and more cost effective in terms of cost, but also in terms of space that it occupies. So this was an example. Going to healthcare application, wearable healthcare devices as well. They are really emerging everywhere nowadays, and the key requirement in this space is cost, but it's also comfort. They need to be user friendly, they need to be patient friendly in order to be embraced and used in the wider population. So a lot of innovation has happened in the healthcare, in the medtech space, which we call Medicine 3.0. And that is really focused on a patient-centric approach, on prevention over treatment, and on personalized, basically, health insight. So it's more a personalized approach that enables for healthcare devices to be more widely used. It needs to be comfortable, but also very often there needs to be disposable. So this, of course, has implications into the cost and into the sustainability, potentially even recyclability. So the next slide, this is just an example of a smart patch for body function monitoring. In this case, you can combine an RFID, like an RFID basically readout system to read all the information, and you can combine it with sensing capabilities for like temperature sensing, or to measure pH sensing and of different body function monitoring. You can think of a moisture sensing, for example, if you want to have a smart wound monitoring system to really check the status of the wound without having to replace the plaster very often. And so all of these are all innovations in the medical space that are enabled by lower cost flexible technology. So while before it was just basically a generic use case, so this is like an actual project that we've done at Pragmatic. This is called Project Straps, and it was developed with an EDUM, the NHS. It was presented at IEEE FLEPS last year. And in this project, we designed and developed and manufactured an ECG sensing patch that was connected with derived from a printed battery, and it was basically providing output to an LED on the same patch. So at Pragmatic, basically, we developed this atrial fibrillation detection. It was a machine learning algorithm that was able to detect an atrial fibrillation event, or like the likelihood of an atrial fibrillation event. So this patch was a heart monitoring patch, was supposed to be wear on the body to constantly measure, to constantly basically check and monitor for an atrial fibrillation event. So this was designed on our second generation, I believe, or maybe even first or second generation technology. So it was quite a few years ago. Has a 13 micron square size. It was running 60 kilohertz. So again, to give an example, and in this case, the chip was basically getting an incoming ECG signal. There was an analog block that was converting into an 8-bit digital output that was fed into the machine learning algorithm that then was providing an output directly to the LED. It was blinking like red or light or green light in case of a likelihood of an atrial fibrillation event was present or not. Another example of a project that we've done recently is the RISC-V. So this was published last year in Nature, just a few months ago. I think it was like October, probably, in Nature in 2024. And this was the very first 32-bit RISC-V microprocessor on Flex. But this was not just basically on a flexible substrate. This was actually demonstrated functional while it was rolled over a pen. So it was like really demonstrated while flexed. So this chip also had 13,092 equivalent gates and was running 60 kilohertz with integrated machine learning capability. And it was done in collaboration with Harvard and Qualcomm. So this type of microprocessor, like the RISC-V in this flexible form factor would be the perfect microprocessor to provide all the computing power required for all the use cases that I just described before, especially in the wearable healthcare space, classification tasks for atrial fibrillation, wound healing, stroke, all of this would be possible with this type of microprocessor, integrated into the same chip in the same flexible system. So to conclude the, let's say, use case section, this is a summary of the main achievements of the last 5 years that we've done at Pragmatic. So this is something that we've, collaborated with several partners. You can see sometimes with ARM, with IMEC, with Harvard and other companies. And this is to show basically the kind of state of the art that is possible with our technology at different point in time, starting from our first generation technology that was on a 0.8 micron at the time, going to our second generation, which was the most recent RISC-V. So this was a 0.6 micron. And then, of course, the third generation, we haven't yet had the time to actually develop and publish anything because it was just recently released. So, just to give an example, an idea of what else can be done and how much you could even improve further with our Gen 3 platform. Next is just a list of all the publications. In case you want to go back and look at them, when you see the video, you can then pause and take a screenshot and look at the details here that you might find some inspiration. And I think now Suman will quickly conclude with some practicalities on how to access the technology.
Yeah. Thanks, Francesca. That was detailed application list. So whatever we have discussed so far, like how do you access this as an MPW service or dedicated runs from your practice is we have 2 ways to do this. First is the you participating in an MPW run. The design space reserved for you would be 3 mm cross 3 mm. Once the wafers are fabricated, usually these are diced and individual dies are picked from your project and packed in a gel box and shipped to you. There are 2 runs right now in 2025 that's scheduled in coming months. More of the timelines would be available in your practice website shortly. Here in the MPW runs, as you know, the mask and fabrication cost is shared between the customers, so you'd get it at a lower pricing. The other alternate is if you want an entire wafer for yourself, it would be participate in the dedicated wafer run, where you would get the entire reticle short space to design. The delivery would be 300 millimeter wafers on glass, and this would be available for you on demand. So whenever you have this requirement, you can go to your practice, they will inform us, and we can sort this out for you. Here a brief summary timeline of the upcoming MPW run on the new Gen 3 platform. And the timelines are not yet on the website, which will be published soon. So the current timeline would be, the registration deadline would be somewhere around June, with the GDS submission deadline around July this year. and then it would be around 8 weeks to manufacture stuffs, dies, pick dies, and ship it to you around September this year. After this, there would be second run as well in September, starting September. So more about the schedules would be available in the website. Yeah, there's also plan to have on-site training at IMEC in Leuven in early September this year. If some of you, I think, would have attended the previous generation PDK training on-site, so it would be something similar to that, but more examples. So there would be seminars from Pragmatic Semiconductor people and other universities. There would be hands-on training using the new PDK with some design examples. And also because we have this new stand cell library that would be available, we will also go through a digital design example with the flow. So that would be interesting. To conclude, the previous webinars that happened 18 months ago regarding our Helvin 2 technologies are on YouTube. You could have a look into it, and more details are there. So this is a continuation webinar. Yeah, that's my final slide. If you have any questions, you can mail it to IMEC's email address, and you can also visit us at pragmaticsemi.com. Thank you for your time.